In the last lesson, we learned how to graph and find the attributes of rationals using the transformational form. That transformational form, remember, was the a in the numerator, b times x minus c in the denominator plus d. This is the transformational form. You can get all the attributes by thinking about how it transforms from the parent functions. Today we're going to focus on what if it's not in that transformational form? How do I get all those attributes? So that's what we're going to work on today. And the first thing you're going to want to find is the vertical asymptote. To find the vertical asymptote, you set the denominator equal to 0 and you solve for that x. That's going to be your vertical asymptote. So you're looking at this denominator right here, 2x minus 4. We set that equal to 0, and then we solve. We're doing that because we're trying to find what makes this undefined. And remember, you cannot divide by 0. So we add the 4 and divide by 2. So x is equal to 2. That's our vertical asymptote. Remember, vertical asymptote is a line, so you have to write it as the equation of a line, so it must be x equals 2. For the second one, again, we take that x squared minus 4 is equal to 0. We need to solve here, and this is the difference of two squares. So you know that you have to factor. This factor should be x minus 2, x plus 2, in order to solve for what's going to make it equal to 0. And so we get x is equal to 2 because 2 minus 2 will make that 0. And x is equal to negative 2 because negative 2 plus 2 will make that 0. Both of these are vertical asymptotes. For our last one, again, we have a quadratic in the denominator. So when we set it equal to 0, we need to either factor, use the quadratic formula, or graph it and find the zeros. Most of the time they can factor, so we'll go ahead and factor. X times x gives me that x squared. Then I'm looking for what multiplies to be that 1 and adds to be 2, and that is positive 1 and positive 1. Since both of those factors are exactly the same, we only have one vertical asymptote there, and that is negative 1, because negative 1 plus 1 is 0. So that's how you find your vertical asymptote. It is easier to find than the horizontal, which is what we'll move to next. So we're going to talk about some steps here in finding that horizontal asymptote. There's a couple rules. It says if the degree of the numerator is less than the degree of the denominator, then it is y equals 0. I want to clarify on some of the vocab there. So degree is the highest exponent in the polynomial. So if the highest exponent in the numerator is less than the highest exponent in the denominator, then it is y equals 0. If the degree of the numerator is greater than the degree of the denominator, so the highest exponent in the numerator is bigger than the highest exponent in the denominator, there is no horizontal asymptote. And if the degree of the numerator is equal to the degree of the denominator, then we are going to divide the leading coefficient of the numerator over the leading coefficient of the denominator. And there's some vocab for you again. The coefficient, remember, is the number in front of the variable. There are slant asymptotes too, and you'll see those in pre-calc. We do have a quick thing to help you remember. We call this Bobo. This one is Botno. And this one is eats DC. So Bobo, Botno, eats DC is the way you're going to hear that most of the time. Bobo, Botno, eats DC. And so what does that mean? So bigger on bottom, y equals 0. Bigger on bottom, 0. Bigger on top, no. So bigger on top, no horizontal asymptote. And then our last one, exponents are the same. Divide coefficients. So bigger on bottom, y is equal to 0. Bigger on top, no horizontal asymptote. And exponents are the same, divide our coefficients. That's how you find the horizontal asymptote. So we're going to look at some examples down here, and we're going to talk about how to do that. You are looking for the biggest exponent. So in this case, the biggest exponent is 2. In this case, the biggest exponent is 2. So this would be considered EATS DC. Exponents are the same, so we divide our coefficients. And the coefficients are the number in front of the x, so that's going to be those right there. We know that when there's nothing written, that is 1. So our horizontal asymptote here would be y equals 3 over 1, which is just 3. For our second one, we look at the exponent. So the bottom one has an exponent of 2 we see there. There's nothing written on that exponent there. And when there's nothing written, we know that's an exponent of 1. That's the one that is assumed when there's nothing written there. So the top has an exponent of 1, the bottom has an exponent of 2. So this is bigger on the bottom. So this is going to be Bobo. Bigger on bottom, 0. So our horizontal asymptote is y equals 0. That's the one you're going to see most often is Bobo, bigger on bottom, 0. And for our last one here, we've got a 2 on the bottom and a 3 on the top there for our exponents. So this is Botno. Bigger on top, no horizontal asymptote, so we would answer no horizontal asymptote. So here, the biggest exponents, they were the same, so we divide this coefficient. Here, our exponent on the bottom was bigger, so this is Bobo, bigger on bottom, 0. And this last one, we've got an exponent of 3 on the top and 2 on the bottom, so this is bigger on top, so bigger on top, no horizontal asymptote. All right, so just to recap, vertical asymptote, you set the denominator equal to 0 and you solve for x. For the horizontal, you follow the rules. All right, the next thing we're going to talk about is holes. And the true math word for that is removable discontinuity. Just doesn't roll off the tongue quite as easy. So holes is what it sounds like. It is like you took your graph and you did a hole punch on it and it's missing that little piece there. That happens when there's an undefined value that cancels out. So that's what we're looking for when we're looking for a hole, or the math term is removable discontinuity. Some calculators will show you the hole if you zoom into that part. So we'll look at that as we go looking at our calculator to see if it'll show it to us. Okay. So we're going to start with an example here and we're going to do all of it. The first thing we're going to do is factor. You know, you can simplify when you factor. This right here does not factor, so I can just rewrite it. On our denominator, we have 4x squared minus 25. That does factor. That's the difference of 2 squares. So we have 2x minus 5, 2x plus 5. Anytime that we have the same exact factors in the numerator and the denominator, we learn that we can cancel those out. And we are left with 1 over 2x plus 5. That's what caused the hole right there when something canceled out. Because in some case, that can still be 0, and 0 times anything is 0, so it would make my entire denominator 0 and the problem undefined at that point. So to find this hole, we take that 2x minus 5 that canceled and we set it equal to 0. It is what canceled. We add the 5 and divide by 2. So there's the x value of my whole, 5/2. To find its corresponding y value, I take what's left and I plug it in. So I took the equation that was left here, 1 over 2x plus 5, and I plugged in my 5/2. The 2's cancel there, so I get 1 over 10. So the whole is going to be found at 5/2 and 1/10. I can go ahead and go to my graph and go to 5/2, which is 2.5, and 1/10, and I can make a little hole there. We just do it as an open circle. To find our vertical asymptote, that's where we get that from our denominator. So I take this 2x plus 5 and I set it equal to 0. I subtract the 5 and divide by 2. So our vertical asymptote is at negative 5/2. I'm going to go ahead and graph that on our graph here. So I go to negative 2/2, negative 2.5, better said. And there is my asymptote. For the horizontal asymptote, that's where I use the rules. I can look up here or I can look at the new one. This is bigger on the bottom because we've got an x on the bottom and none on the top. Again, you see that here, we've got an exponent of 2 and an exponent of 1. So this is BOBO, bigger on bottom, 0. So our horizontal asymptote is going to be at y equals 0. All right, if I'm graphing this now without a calculator, I'm going to want to do a table of values. And I would want to pick points to the left and to the right of that vertical asymptote so I can see where the pieces of my rational end up. So I'm going to go to negative 3 and negative 2 on the x. That's to the right and to the left of that vertical asymptote. I take that negative 3 and I plug it in right here. That gives me negative 6 plus 5 in the bottom, which is going to give me negative 1. I take this negative 2 and I plug it in for my x there. That gives me negative 4 plus 5, which is 1. 1 divided by 1 is 1. So I'm going to go ahead and graph those points. At negative 3, I've got a point at negative 1. And at negative 2, I've got a point at positive 1. And then remember, our asymptotes guide our graph behavior. So we are going to just move towards the asymptotes there. And there's my graph. The last thing there is the domain and range. Remember, domain is our x value. So I'm going to start over here from the left. I am jumping over that asymptote, and then I jump over that point and keep going. So our domain would be all real numbers except for our vertical asymptote, which is at negative 5/2, and our whole, which is at 5/2. You have to remove both of those from the domain since we are jumping over them. So this is the x value of the whole, and this is the vertical asymptote. For our range, we start at the bottom. We're hitting all of these points on the graph, and then we jump over that horizontal asymptote. We start hitting points, and then we jump over that hole and keep going. So our range would be all real numbers except for our horizontal asymptote, which is 0, and the y value of our hole, which is 1/10. So there it is. It's got a lot of pieces, a lot of attributes that you have to think about. But if you go step by step, it is not that difficult. So let's look at it on a calculator now so you see what's happening when you do this on a calculator. I can use alpha y equals to get that numerator over denominator. That allows me to put it into the calculator exactly the way we see it. And sorry about that, there's a glare there, so I'm going to go ahead and fix that. See where you can see that best. Okay. So now I'm going to put in my equation, 2x minus 5 over 4x squared minus 25. That's the original equation that we're putting in there. Oh, there we go. That's much better. I'm going to go ahead and y2, and I'm going to put in the simplified equation. So I'll put in that 1 over 2x plus 5, just so that we can look at some things. There is our equations. I hit graph, and it should come out exactly the way we had it on paper, which it is. There you go. And then that red one that's coming over it is the simplified version. So you see that they are exactly the same graphs that we have in there. The y1 and the y2 are right on top of each other. It's just the simplified. That's an easy way to check to see if you simplified it correctly. I'm going to turn off that second one for a second. And I'm going to go ahead and zoom in. I'm going to zoom in really close here to see if we can see that hole on our calculator. And sure enough, there it is. So you see there's a break in the graph there. That's that removable discontinuity, the hole. If you zoom in close enough, you'll see that the calculator does skip over that part. It's not continuous there. That's that little hole that we punched out of the graph there. All right, I'm going to go ahead and turn this back on and then now look at our table. So our table of values here has a bunch of points and we don't see the error. That's because it was a fractional value for our vertical asymptote and our hole. But if I set my table to go to negative 2.5, which is where our vertical asymptote is, and I go to the table, I will see the error there. That's our vertical asymptote. Remember, that's what makes it undefined because we divide by 0. So that's why it says error there. If I go to the positive 2.5, in the original equation, you're going to see that it says error because that's where we determined it was going to make it undefined. In the newer simplified one, there's the 1/10, which we found to be the y value of the hole. So there's some resources on your calculator that you can use to graph this and to find the values on your table. If it stays as an error, then it's a vertical asymptote. If it's an error and then tells you the number, then it is a hole. So there's another way of determining those. All right, we're going to look at a second example here. We have 2x squared plus x minus 1 over x plus 1. First step is to factor this. Once I have factored it, if we have the same exact factors in both the numerator and denominator, that cancels and we're left with 2x minus 1. We do have a hole because something canceled, so I take that thing that canceled and set it equal to 0. That's x plus 1 equals 0. When I subtract the 1, we get x is equal to negative 1. So the hole is going to be found at negative 1. I plug in my negative 1 to my leftover equation there so I can find the corresponding y. That is negative 2 minus 1, which is negative 3. So the hole in this case is at negative 1, negative 3. Just take it and make a little open circle there. It looks like you took a hole punch and punch that point out. Now we look for our vertical asymptote. There is nothing left in the denominator, so there's no vertical asymptote. When we look at our exponents, this is bigger on top. This has a 2 and this has a 1 as an exponent. So this is botno. Bigger on top, no horizontal asymptote. So we have no horizontal asymptote here. which we should have known because what was left here is a line. So this is just a linear equation with a slope of 2 and a y-intercept of -1. So we start at -1 and we use our slope of 2 to go up 2 and to the right 1, or down 2 and to the left 1. So this is just going to be a linear equation with a hole in it. Like that. That's about as easy of a rational as you can get. It would be all real numbers except for that whole piece, which is at -1, and all real numbers except for that -3. All right. One last one. This one's going to be a little bit harder. First thing I would need to do is factor this thing. We've got the difference of squares on top. We've got a GCF of x, so that's going to have to come out first, and then I'm left with x plus 2 and x minus 1. The x minus 1's cancel, so I'm left with x plus 1 over x times x plus 2. This has created a hole wherever x minus 1 is equal to 0. So I add the 1 and I get x equals 1, so this gives me that. I plug in the 1 here so I can find my corresponding y value. That gives me 1 plus 1 over 1 times 1 plus 2, which is 2/3. So the hole is going to be at 1 2/3. There it is. This has two vertical asymptotes because there are two things that will make that 0, when x is 0 and when x is -2. So that's got two vertical asymptotes. And we would graph both of them. We've got one at 0, and we've got one at -2. For our horizontal, we look at our exponents here. This is bigger on bottom, so that's going to be Bobo. Bigger on bottom is 0. And so this is kind of a strange little graph. In order to do it without a calculator, we would have to get more points than just the original ones that we got on that first one, because we need points to the left and right of each one of our vertical asymptotes. And since there's so little space in between these two, we're going to have to figure out what is going in this middle. So we're going to need several points for that. So I'm going to get -3, that's to the left of the vertical asymptote, -1, that's to the right of the vertical asymptote. Then I need one to the left of the other vertical asymptote. So I'm going to do -1/2, and then 2 to be on the right-hand side of that other vertical asymptote. And so I plug in those points to get the corresponding y values, and I get -2/3, 0, -2/3, and 3/8. Not the best points to graph, but they are some points that we can graph. So we've got -3 and -2/3 would be right here. And then I just move towards the asymptote. So we're going to have a piece that looks like this. In the middle, we've got a point at -1, 0 right there. And then we've got one at -1/2 and -2/3. Since our graph has to move towards the asymptotes, then it is going to do this right here. And then our last one here, we've got one at 2 3/8. And again, we move towards the asymptote. We're going to skip over that little hole and move towards the other asymptote. So this is a pretty cool rational there. We wanted to show you this one because at the ends there, our horizontal asymptote is guiding our graph. So it's getting closer and closer to that 0. Same thing on this side. In the middle, it is crossing that horizontal asymptote. That doesn't happen often, but the horizontal asymptote can be crossed at some point in the middle like this. At the ends, it is still guiding our behavior, so it's going to get really close but not touch. But in the middle, it is crossing right there. Your vertical asymptotes are never going to cross, but the horizontal sometimes does. So for our domain here, we would have all real numbers except for -2, 0, and 1, because those are all the things that make our denominator 0. For our range, this one can be tricky. We're looking at our y values, and so as it's coming from the bottom here, we usually jump over the asymptote, but in this case, it's touching the asymptote right there. So we do have a y value at 0. We would not exclude that. The only one that we would exclude, actually, we can't exclude this one either. If you think about the whole, the y value is not touching it here, but it is touching it right here. So because of this middle graph, I have every single y value. So we have nothing to exclude here. So we would just put all real numbers, and that's it. Because it does have every single y value. That's graphing rationals that are not in the transformational form. They're a little bit harder than with the transformations from the parent functions, but they're very doable. Just make sure that you remember those rules for finding the horizontal asymptote. That's Bobo-Botno eats DC. And that the vertical asymptote comes from whatever makes the denominator 0.